Welcome. Good morning. We're going to review geometric mean, Pythagorean theorem, and special right triangles. So I've already taught this to you. It should be a review. It is recorded, so you can rewind it as you need to. Let me get to the next slide somehow. There we go. So I put in a little joke here. They forgot the Bermuda Triangle. We're going to start with geometric mean because that was the first thing that we learned. So just a reminder that the geometric mean works with right triangles when you draw the altitude within them. So you can see I have those right angles showing that. X, Y, and Z are all the geometric means in this picture, and the parts of the hypotenuse are 3 and 12. So therefore, I would know my whole hypotenuse would be 15. If I look at X, X is the geometric mean that's going to go with A and B. So I can write my proportion so that X is diagonally across from itself with the two pieces that it goes with, A and B. Y is a geometric mean that goes with A and C, and Z is the geometric mean that goes with B and C. They all go with different combinations, and you should keep that straight to write your proportions. Here we have an example. We're using the 3 and the 12. I'm going to go right down the middle with the geometric mean of X. When we write it, we write the X's diagonally because it is the geometric mean, and we write the other two pieces, 3 and 12. We multiply to get X squared equals 36, and then we take the square root to find that X, which in this case is the altitude, and the height is 6. If we look at Y goes with the piece of the hypotenuse right around the corner, which is 12, and then the entire hypotenuse, which you can see that I wrote in red, is 15. So that may not be in your picture. You may have to write that in order to figure it out. So Y is the geometric mean. It goes diagonally across from itself. The other two are 3 and 15. Multiply that together and you get 45. Take the square root of it. And moving forward, we're just going to hit the square root button with geometric mean. We've been simplifying them. I know we've been struggling. So we're going to make it a little bit easier and just use your calculator to get it to 1 decimal. When we look at our Z geometric mean, that goes with 3, the piece right around the corner of the hypotenuse, and the entire hypotenuse, which is 15. I set that up in my proportion. Multiply to get Z squared equals 180. Take the square root and we get 13.4. Switching over to the Pythagorean theorem. You all know the Pythagorean theorem before you came in. Just a few reminders. It's used to find the sides of a right triangle. And make sure you have C as your hypotenuse. So it's always across from the right angle. You may have it or you may not have it, but make sure that it is A squared plus B squared equals your hypotenuse squared. In this example, my legs are 5 and 9, and I'm trying to find my hypotenuse. So I have 5 squared plus 9 squared equals x squared. Square those, and I get 25 plus 81 equals x squared. X squared is now 106. And again, we're just going to hit the calculator button. I rounded to 2 decimal places and got 10.30. In the second example, we have 10 squared plus x squared equals 22 squared. We square it, we subtract the 100 to get 384. Notice I didn't do 10 squared plus 22 squared because 22 is the hypotenuse. So that's what I mean by you have to make sure you put it in the right spot. We use our calculator to take the square root of 384 and we get 19.6. We can do Pythagorean theorem when we have some word problems. So here we have 2 joggers running 8 miles north and then 5 miles west. What is the shortest distance they must run to return to their point? So the first thing we would do is draw a labeled picture. So we would run 8 miles north, 5 miles west. We want to try to draw that. I gave you a compass in the bottom corner to help you out. And it should look like this. We can use our Pythagorean theorem. 8 squared plus 5 squared equals x squared. Square those numbers. X squared is 89, and we can turn to our calculator to get 9.4 miles. Switching over to special right triangles. We had 2 different types. We're going to start with 45, 45, 90. We introduced this in class and we did struggle a little bit with this. And in this case, we are going to stay with the square roots because that's where you see the pattern. So one piece we have to figure out is how do I even know that it is a 45, 45, 90 triangle? You can see in the green one that we have 2 congruent angles and the other angle is 90. Therefore, those must both be 45. You can see in the red triangle that both of the sides are marked congruent. So it's an isosceles right triangle. If it's an isosceles triangle, then the both base angles must be the same. So they would both be 45. And then in the purple triangle, we have one angle that's 45, one that's 90, therefore the other must be 45 as well. Any of those markings would be enough to move forward and use these side ratios. So let's start. We have our green triangle with a leg of 5. I don't know the other leg is x, and we're going to call the hypotenuse y. Well, it is a 45, 45, 90 triangle, so the legs are the same. So I do know that the other leg is 5. So I can do 5 squared plus 5 squared equals y squared. Multiply those out, add them together, and I get 50. And then we have y equals the square root of 50. If we were just to take the square root of that and it would become a decimal, we wouldn't necessarily notice the pattern, but the square root of 50 has a perfect square of 25 in it. So we can take out the square root of 25 as a 5 and it becomes 5 root 2. Therefore, the sides of this triangle are 5, 5, 5 square roots of 2. That's a pattern. If one of the legs was 6, the legs would be 6, 6, and the hypotenuse would be 6 square roots of 2. If you didn't remember this, you could still always do the Pythagorean theorem, but it is a nice pattern to be able to provide you with a shortcut. So this is the ratio of the leg to the hypotenuse is 5 to 5 to 5 square roots of 2. The generic one is 1 to 1 to 1 square roots of 2. Here we have 3 examples. In example A, the legs are 18. In example B, the legs are 30. In example C, the hypotenuse is 20 square roots of 2. Hopefully you can figure those out. In A, we have 18, 18, so the hypotenuse is 18 root 2. In B, we have 30, 30, so the hypotenuse is 30 root 2. And in C, we work a little bit backwards. My hypotenuse always has to be the longest part, so it has that extra multiplier of root 2. But the number in front of it is 20, so both of my legs are 20, so that my ratio is 20, 20, 20 root 2. Switching over to the 30, 60, 90 triangle, we need to know what it looks like. So I'm going to actually start with an equilateral triangle. This is a red triangle. All the sides are 10. That bottom little line there is supposed to be a congruent mark. We have our equilateral triangle with the height drawn and a one side of 10, which means all of the sides are 10. So if all the sides are 10, then the bottom 2 halves are each 5. My angles are all 60s, but at the top, since I've drawn the height, those are cut into 30s. And then I'm going to pull that out, and here's where the 30, 60, 90 triangle comes from. So my littlest angle is 30. That's up at the top, and that's across from the littlest side, in this case 5. My hypotenuse is across from my right angle, and you can see it's double. So the short side, if you double that, you'll get your hypotenuse. If you have your hypotenuse and you cut it in half, you'll have your short side. So it's the side across from the 60 that is a little tricky. But because we have 2 sides of a right triangle, we can use the Pythagorean theorem to figure out what x is. So when we write that, we get 5 squared plus x squared equals 10 squared. 25 plus x squared equals 100. X squared equals 75. Again, if I hit the decimal, I'm not really going to recognize the pattern, but if I take the square root, there's a perfect 25 in there. So this becomes 5 times the square root of 3. Well, 5 was my short side. So the pattern is whatever your short side is, put it with the square root of 3. So the pattern becomes short leg to medium leg to hypotenuse is 5 to 5 square roots of 3 to 10. Generic, small to medium to hypotenuse, is 1 to 1 square roots of 3 to 2. So if we look at this example, if I have 8 on the side across from the 30, that's my smallest side. My medium side would be 8 times the square root of 3, and my long side would be 16. In triangle B, I know my hypotenuse is 40, so I can cut that in half for my y, and my y ends up being 20, and my medium side is 20 root 3 for a ratio of 20 to 20 root 3 to 40. So just to compare those, 45, 45, 90 side ratio, angle ratios have the side ratio of 1 to 1 to square root of 2, where 30, 60, 90 is 1 to 1 square roots of 3 to 2. In the 45, 45, 90, the square root is on the hypotenuse, but in the 30, 60, 90, the square root is on the medium leg. In the 45, 45, 90, the legs are congruent, but in the 30, 60, 90, the small leg is half of the hypotenuse. So just a few things to keep in mind. Hopefully that was a good review for you. We've looked at geometric mean, Pythagorean theorem, and special right triangles, and we will have an upcoming assessment on this. Good job.